Hello everyone. Welcome back to our YouTube channel. Thank you for watching. I would like to take you through my machine learning project, which is about explainable graph neural networks for heart disease prediction. And I'm by names of Kavma Hamza and my colleagues Namuto Sidayan and Kalemala. Below our details and our affiliation is Macquarie University. So the contents of the presentation include the introduction, the related work, the problem statement, the research questions and objectives, the research contributions, the methodology, the dataset, the experimental results, the conclusions, limitations and feature works, references, and the acknowledgement. So I'll briefly take you through the introduction, the related work, the problem statement, and the research questions and objectives. So the introductions, according to World Health Organization, it's estimated that cardiovascular diseases are the leading cause of death globally, taking an estimated 7.9 million lives each year. So more than four out of the five CVD deaths, the cardiovascular diseases are due to heart attacks and strokes. This calls for early detection and intervention to reduce the risk of sudden heart failure and improving patient outcomes. So this is where our project comes in. So unhealthy diet, physical inactivity, high body mass index, high blood glucose, and tobacco smoking, which contribute to half of the global burden of the heart disease. So the related works, Rishi, Dubey, and colleagues analyzed various machine learning methods for forecasting heart disease and determined that neural networks are effective for this purpose. Similarly, there is also another team, Ashishi Chabibi, conducted experiments with data from the UCI repository using data mining techniques to predict heart diseases. They employed the K-means algorithm and Bayes. So the problem statement. So the black box nature of GNNs poses a significant challenge in interpreting and understanding the decisions made by these models. Due to this, we seek to implement interpretability of these using SHARP and LIME. So our research questions and objectives are to explain individual predictions, to summarize global interpretability, to compare different methods, to improve model trust and transparency, to ensure fairness and robustness, to provide human understandable explanation. So I would love my colleague to take on from here to take you through the research contributions and the rest.
Hello, my name is Namtos Diana, and I'll take you through the next slides from the research contributions. Yeah, one of our the main contribution now we have done in the project is implementing the explainability of the models, the graph neural networks, and we achieved this using the XAI techniques, which is LIME and SHARP. And this explainability contributes to interpretability of the models, and this leads to, it provides trust and transparency of the models produced. And yeah, this helps the clients, like when you're explaining how a prediction has come about, you are able to explain to the patient or the client that you have this you're likely to get heart disease because of such and such what features. And also just creating a benchmark of the interpretable GNNs, since most of them have not been implementing explainability. So our methodology, we started by obtaining the data set, which we got from the UCI repository. And we start by processing the data. After processing it, we are going to feed this processed data into the model, the features of the data set, and then the normalized vector are fed into the GNN models, which is then worked on to give our predictions. And then we use these predictions and some of the features to feed into the XAI techniques to bring about the explainability of these models. And then after explainability is done, that's when we get the output, whether the person is at risk of getting heart disease or not. And then also the explainability, like which features contributed more to the prediction. So the data set, as I've mentioned before, we got it from the UCI repository, and it has 12 features, including the target. And these are the variables, the features that we are using So from the EDS, these are some of the visualizations we have, the age distributions of the patients, and see that most of the people are between the age of 50 and 60. And then for the gender, we see that most patients were male compared to females, and that's why we have used a SMOT to bring about the balance of the data sets. And then we see that here, this is a pie chart representing the percentage of people who had at risk of getting the disease, and those who are not. The normal is 53%, and those that had the disease is 47, and these are just the numbers. So this is just a representation of the features that contributed more, which is the chest pain type. It has 4 groups. And then this is the heat map. The lighter ones show them highly, positively correlating features to the predictions. So we see that here, chest pain type and ST slope are the ones that are contributing highly to the disease. And these are the results that we got. For the GNNs, the most performing GNN was the GCN, and it has an accuracy of 90. And we see that GAT and GraphSage also has, we have 80 and 85 accuracies. And then you may see that these other models, the traditional models, are also having high accuracies. But when it comes to performance, we find that the GNNs are still giving more accurate predictions than the traditional machine learning models. And these are just the representation of the confusion matrix values, the true positives and false positives. This was for the normal trend, and this one on the right is for the when we applied SMOT, but we found that it wasn't giving any much differences. It was either giving the same accuracies with the normal, and also like in some cases, for example, when you see GATIA, it had 85, but on applying SMOT, we got 80. We have also for GraphSage is the same, and also we applied BSMOT, and these are the results we got. So yeah, my colleague will take you from there. Thank you very much.
Hello, this is Kalema Alan, and I'm going to talk about the results visualization. In our research, we implemented the explainability using Sharp and Line, and this first diagram you're seeing here represents the Sharp feature importance visualization. It shows the different features and how they contribute to the predictions in Sharp. As we can see that ST slope contributes a high output of 0.3, the highest output. Okay, it contributes highest to the output, and the next is old peak. Whilst this side we see chest pain, the blue shows those that are not correlating with a positive prediction. So, and in our data set, we also try to bring out the visualization in prediction. So we use the force plot on certain models, for example, on certain predictions. For example, we used the sample instance of 100, and we fed it into the data set. It came out with a prediction of 1, and the force plot here shows the visualization, shows the feature importance and to what percentage they contributed to the prediction. As we see that the features that contributed to the prediction of 1, we had max heart rate, the sex, chest pain, angina, and ST slope with a percentage of contribution, or odd peak contributed otherwise. So those are the key features the model based on when it was doing that instance. So down here, this is also a visualization, just as we've seen one behind before. It shows the feature importance of a certain model in overall, and how they are ranked. That age is ranked as the least of all the features when predicting. So we have other models. We used Lime on other models, and Lime didn't use a force plot. We used the pie plot instead, and it shows the same thing. As you can see, the green that go to the right indicate the positive correlation, like features that contributed to the positive result, or red contribute otherwise. So this, in our model, used GraphSage, for example, used a Lime explainability. So this is how its feature importance was declared. This is the same thing as the other, though more detailed. For example, here they provide certain values to the features that were used in clarification. Yep. Here we have the conclusion. So in conclusion, we demonstrate the effectiveness of the graphical networks in predicting heart disease outcomes. So here, by emphasizing explainability, our approach enhances the interpretability of the prediction, thereby facilitating clinical decision. So in future research, we may explore an integration of clinical variables and deployment of the model in real-world healthcare settings. And the limitations, one of the limitations we had was data conversion, converting the data we had into the format that the model receives. For example, the network format for some model, and model explainability, implementing explainability on certain models was also a problem. And data set characteristics, some characteristics of the data set did entirely reflect the real-world doctor-patient setting. So in recommendation, we're exploring a more scalable technique compatible with many architectures, enhancing the model performance. For acknowledgement, we appreciate Mr. Galiwango for the supervision throughout the whole project, UCI for availing the dataset, and Makerere University for providing the resources. Thank you very much. Thanks for watching.